Okay, hi guys. Okay, welcome to the lecture of ComNets 3. My name is Tung Ho Yu. Yeah, it's good to see you again. As I said yesterday, I will give you a lecture for the latest protocol of low latency adaptive streaming. Especially, I will introduce the latest protocols. First, I'm gonna review the previous lecture briefly. Yep, and then let's discuss the latency solutions for the ABS. And actually, there are many streaming protocols to solve the latency issue. Among them, let me introduce the popular ones such as Common Media Application Format called CMAF and web real-time communications called WebRTC. And finally, I will give you some additional information about advanced video streaming, such as 360-degree video streaming. Yeah, good. Okay, let's start from the review of the previous lecture. First, I will introduce more about MPEG-DASH. Actually, yesterday, I didn't explain the details of MPEG-DASH, although this is very important to basically understand the current video streaming platforms such as YouTube, Netflix, and Amazon Prime Video. So let me introduce the details of MPEG-DASH first. Actually, in order to understand the MPEG-DASH, we should understand MPD completely. MPD means that maybe you remember that media presentation description. As you can see, the international dash standard also focuses on only MPD here, and MPD here, and its segment formats. So this is very important to understand the MPEG-DASH. So this means that understanding the MPD structure, that is period, adaptation set, and representation and segments, is the most important. And so if we understand the MPEG-DASH, we can also understand other streaming formats and other streaming protocols, because most of the latest protocols are based on the MPEG-DASH. So this is very important to MPEG-DASH and its MPD. And also, without receiving and parsing MPD here, without parsing and without receiving MPD, we cannot request even one segment to the YouTuber server. So we can just simply think that MPD is everything. Yeah, MPD is everything for about MPEG-DASH. That is adaptive streaming. So now let's dip into the MPEG-DASH. As I said yesterday, the MPD is manifest, and has such hierarchical data structure. Here, manifest means that a list of goods or passengers. Yeah, this is from Oxford Dictionary. Anyway, in one period here, there are many adaptation sets. You remember that, right? And each adaptation set refers to a media components such as video and audio. And in one adaptation set, there are multiple representations like this. That refers to the quality. And in each representation, there are multiple small segments like this. There are real transmission data from the server. That this is the hierarchical data model of MPEG-DASH. So let me give you some questions. In this figure, how many adaptation sets are there? Yeah, just a guess. In this figure, how many adaptation sets are there? Nobody? Yeah, anyway. Yes, right. There are 3 adaptation sets for the video and audio 1, for the video and audio 1 and audio 2. Yeah, there are 3 adaptation sets. Then how many representations for audio 1? Yeah, there are 3 representation blocks for the surround and 128 kbps and 48 kbps. Yeah, good. Then now let's dive into this. Okay, assuming that device a device starts streaming the contents by recasting segments of video bitstream at the highest available quality 5 megabps and the English audio at the 128 kbps here. And for instance, for instance the device doesn't support the surround audio, so the device recasts the English audio. After streaming the first segment of video and audio, and after monitoring the effective network condition, the device realized that the actual available bandwidth is lower than 5 megabps. So at the next available switching point here, it switches the video down to 2 megabps by streaming the next segments from the mid-quality track while continuing streaming of the 128 kbps AAC audio. Like this, according to the user channel status and device capability, user client can recast different quality of multimedia segments adaptively and dynamically by using this MPD. So now let's see one basic MPD example. As you can see, there is only one adaptation set, only one adaptation set here, which means that there is only one multimedia component to be delivered. And you can see that this component is actually a video component here, and that is compressed by SHVC, and it uses MP4 container. Actually, this is the code. Yeah, so we can use the in the adaptation set, and there is one representation by using MIME type. We can define this is the video, and then they use the MP4 container. And then by using the codec identifier, we can use this video component compressed by SHVC. So actually there are something like code. So actually this code denotes the SHVC, and it is defined in the MPEG-DASH standard. So according to your application, we can choose which compression method we will use, according to your applications. So this is so simple, right? Actually, this is the basic structure of MPD. Let's see one more example. I think now you can understand this MPD without my help. Anyway, first there is one adaptation set including a video component, with the MP4 container. And in this adaptation set, there are two representations. This is the first representation from here to here, and here to here, the second representation. And the first one is for 2K. The resolution is 2K resolution, and the other one is for Full HD resolution here. And in addition to this, bandwidth also can be defined like this. Yes. And then actually that are the difference from this is the only difference from the previous example. I'll give you some seconds to have a look at more. We can actually, as I said, this is a hierarchical model. So we can start MPD, and this is the first period. And in the first period, there are adaptation sets. And then in the adaptation sets, there are two representations. And then we can define the quality of the video component like this and like this. Easy, right? Okay, good. So far we review about details about MPEG-DASH. So then we have to back to the latency issue. So then what is the latency? Yesterday I introduced this is the time delay between the cause and the effective response. This is the latency. Usually these blocks make the latency in the video streaming, encoding and containing, storing, propagating, and decoding and displaying and so on. These blocks make the latency in the video streaming. Especially on the encoder side, the encoded segment can be transported only after finishing the encoding, like this and here. Again, the encoded segment can be propagated only after finishing the encoding process. That's why at least the delay as long as the segment time is inevitable. Yeah, this is the latency issues of the ABS, like MPEG-DASH. Therefore, yesterday I said a bigger segmentation imposes more latency. Again, bigger segmentation imposes more latency. This is what we learned yesterday, right? So good. Then now let's see about the latency solutions of adaptive bitrate streaming, ABS. Let me introduce again these blocks where the latency occurs. Let me consider the blue block as an encoder, and the CDN is a server, and the framework and display are the decoder. I only introduced MPEG-DASH only, but there are many types of streaming protocol. Apple's HLS, MPEG-DASH, Microsoft Smooth, and Adobe's HDS, and so on. Yeah, nowadays there are many live stream protocol using HTTP based on the HTTP. Even if the same video here, even if the same video source, the content provider like YouTube and Netflix have to make many types of content using different streaming protocols and different containers. This is because the CDN server here, because the CDN server has to include all of the different user devices. For instance, in the case of Apple devices, HLS is used for mainstream protocol. On the other hand, Microsoft Smooth is used for the main in the Microsoft devices. And then the MPEG-DASH is an international standard. Yeah, that's why CDN server has to embrace all of the different user devices. So it takes much time to make the copy and encoding and store in the CDN server. Yeah, this is so terrible. Therefore, many industrial companies, especially Apple and Microsoft, proposed a new standard together. They attached great importance to the merging of existing streaming protocol based on HTTP. And they call it Common Multimedia Application Format, CMAF. And finally, CMAF was chosen in an MPEG international standard in 2018. If the content provider like YouTube and Netflix use the CMAF for their content streaming, we can kill the complicated things. It's very simple, right? And only put the CMAF here, and so we can reduce not only encoding cost but also storage and packaging cost. And this makes more efficient edge caching in the CDN server like this, and consequently we can overcome the latency issues because we cut unnecessary encoding process. Yeah, it's more simpler. It's more simple than the previous complicated ones, right? So in summary, we can CMAF allows a single container, but CMAF allows a single container, but manifest will differ. It means that CMAF uses the single container like MP4 or TS, but manifest will differ. They can use MPD of MPEG-DASH or other things. This is the main difference from the MPEG-DASH using the only one manifest MPD. For instance, even if only one container is to use the encoder, they only use the TS container. The CDN server can provide different manifests in accordance with the user capability. There is MPD like this. MPD is for Android, and another MPD is for the Windows. And then the M3U8, this is the manifest of HLS, Apple's. So M3U8 is for iOS and Mac users. So this is the main concept of CMAF. And then so far we conceptually checked one of the solution for reducing the latency through the CMAF. So from now, let's dive into the CMAF. What is the CMAF? What is the advantages? And then what is the structure of CMAF? Let's see that. As I said, the conventional HTTP-based streaming protocol such as DASH use the fragmented MP4 structure we call FMP4. As you know, this allows coupling media data MDAT and move fragment MOV. Here, MOV is an index for particular segments to download and play back. This is like metadata. So just simply, we can think that the MOV here, MOV is MPD of dash. So we can just simply think that MOV is the MPD. And then MDAT here, MDAT is media data such as raw video and audio information and time-based element like subtitles. As you can see that in the case of CMAF segments, and this segment is divided into multiple small chunks, and each chunks can be decoded and played independently. So every single chunks there is a move. This is the main difference from the conventional FMP4 like dash. For instance, even if these gray colored here, even if these gray colored chunks are still being encoded and multiplexed in the encoder side, we can load and play the blue colored chunks. This means that the playback of CMAF chunk can be started once the first chunk is received. So the player already plays on one end while the encoder still writes on the others. So this is the main difference as compared with the traditional fragmented MP4 segment. So let's see one example. The upper one, this one. This case is MPEG-DASH, and the other one is the case of CMAF. As I said, CMAF allows dividing the segment into multiple chunks. For instance, when we consider a segment of 2 seconds, we can divide into 4 chunks like this with 500 milliseconds. And then, as I said, a large segment imposes the longer time delay, the high delay. Therefore, thanks to the CMAF chunk, we can receive the third segment more quickly than the conventional dash. Okay, let's see one demo sample. I think this is good to understand what is the difference from between CMOF chunk and the MPEG-DASH segment. Okay, as you can see in the below here, CMOF chunks can be propagated upon finishing the short encoding process. On the other hand, for the conventional live streaming, we have to wait until the encoding is over. Okay, can you feel the latency difference? Okay, let's do one more of that. Okay, encoding and propagating immediately, but it's still encoding, and then done propagating and buffering and play. Yes, this is the main difference. In the case of a CMOF chunk, they can decode and play immediately, but in the case of MPEG-DASH segment, we have to wait until finishing the encoding process, as I said. So yeah, this is the main difference. Okay, good. And then let's see the structure of manifest of CMOF. Actually, it looks very similar to the MPEG-DASH one, right? In fact, the CMOF does not define a manifest, but any manifest can be used to can be used for the CMOF media object model. I thought it should be possible to use similar figures to MPEG-DASH like this, but with CMOF terms and definitions. Since this is just an example for you, every possible and use case is not reflected here. For instance, actually, period in dash are presentation in CMOF, but there is no concept. There is no concept of a presentation defined in CMOF, so it is assumed to be defined in the actual manifest. Okay, anyway, each CMOF presentation may contain multiple CMOF selection sets like this. For component selection such as video, audio, and subtitle languages. And CMOF selection, yes, and each CMOF selection set may contain multiple switchover CMOF tracks, and thus is renamed to switching set. The functionality of selection set and switching set of CMOF is implemented as adaptation set within Dash. A CMOF track and the CMOF track here, and the CMOF track basically correspond to a Dash representation switchable within a CMOF switching set or Dash adaptation set respectively. And the Dash initialization segment are referred to as a header in CMOF. And CMOF fragments are basically Dash segments from an abstract point of view. And also CMOF defines segments and chunks as well as the term CMOF resource and CMOF track. A CMOF segment may contain multiple CMOF fragments, but no CMOF header. A CMOF chunk is basically a sequential and contiguous subset of CMOF fragment enabling low latency streaming. So similar to Dash segments, the CMOF resource can be identified using an identifier such as URL. And a CMOF track file contains both CMOF header and fragment like this. And CMOF tracks are independent. That is, CMOF tracks contain only CMOF fragment of the same media stream, no multiplex contents, and strictly synchronized with each other to facilitate the bitstream switching, such as the core functionality of dynamic adaptive streaming. However, this also requires that all CMAF fragments need to start with independently decodable media data within a switch set such as iframe. Again, this also requires that all CMAF fragments need to start with independently decodable media data within a switching set such as iframe. Maybe you remember that what is the iframe, right? Okay, good. So actually this is very similar to Dash, right? That's why I emphasized the MPD structure in the beginning of this lecture. Yeah, so it's very this concept is very similar to MPEG-1. Good. So let's summarize it about CMAF. First, CMAF chunk is a big feature for the low latency, and CMAF can also reduce the cost such as encoding and packaging cost, deploy complexity, storage cost, and so on. And finally, CMAF has super backward compatibility because it embraces both MPEG-DASH and Apple HLS in the same container. This is the main point. Again, CMAF can embrace both MPEG-DASH and Apple's HLS in the same container. Yeah, this is the main point of CMAF. Okay, good. And from now, let me introduce one more streaming protocol. Actually, so far we learned about CMAF to overcome the latency issues of ABS. Yeah, this is one of the best solutions to overcome the latency issue. And then the other one is WebRTC. Actually, WebRTC is very popular nowadays. So let's dive into what is the WebRTC. Good. Actually, WebRTC is real-time communication protocol on web browsers and mobile applications. Sorry. and it is free and open project that support HTML5. And this is super fast, less than one second. And this is faster than CMAF in terms of streaming latency. As I said, less than 1 second here. But in the case of CMAF, between 1 and 5 seconds. And WebRTC commonly used for video chat or conferencing, such as Skype and WhatsApp, Google Meet, and Cisco WebEx, and so on. I'm not sure, but this lecture system, blah, blah, anyway, maybe this lecture system may use the WebRTC, I guess so. I need to check it. Anyway, so nowadays this is WebRTC is very popular. Anyway, and WebRTC is based on the peer-to-peer networks such as one-to-one P2P and mesh P2P networks like this. So now let's more details about how to make the core using WebRTC. Actually, there are 5 steps. First, if client A here, yeah, they use the Chrome. If client A wants to make a call with the client B, so client A has to send his information to server. Like, hey, I need to talk to client B. Here is my information. So, and then after that, the server informs client B, like, hey, client A wants to talk to you. Here is client A's information. Do you accept? Yeah. And then if client B accepts it, client B will give one information to the server. Sure, here's my information. And then the server forwards that information to client A. Here is the client B's information. When that happens, we get the line over here. We can send any type of data, such as voice and video and something else. So maybe if there are people who know VoIP, they will say, this is very similar to the VoIP process. Yes, right. This is very similar to, and this is very like session initiation protocol SIP of VoLTE and VoIP. Yeah, this is very similar. Actually, there's nothing new here. Yeah, there's nothing new here. But I could never send a message directly across web browser. This is only fundamentally different how browsers work after the WebRTC. This is the main point we need to remember. They can communicate with each other directly without origin server. Of course, the server has to be a bridge of them for the session initiation. But after that, without the origin server, they can communicate with each other directly. Yeah, this is the main point. So we can say from number 1 to 4 is not WebRTC steps, but we can say this is signaling of WebRTC. And only number 5 belongs to WebRTC. And currently, WebRTC is supported by such browsers: Chrome, Firefox, Opera, Edge, Safari, and so on. Good. So, and even when we consider the WebRTC for the live video streaming, WebRTC much faster than Dash or CMAF because it only needs RTMP ingest here, which simply means the signaling. But in the case of MPEG-DASH and CMAF, there are many processes here. Yeah, it's totally different, right? Yeah, the WebRTC just collect information such as API, identify, and the type of data, security, and so on. However, in the case of WebRTC, there is no MBR streaming and no ABR streaming like Dash and the CMAF. Here, MBR means that multi-bit rate, and ABR means that adaptive bit rate. There is no ABR and MBR in the WebRTC. This is the main difference. So in summary, in terms of latency, WebRTC is much faster than CMAF because of simple communication process. But this scalability of WebRTC is weak rather than CMAF because CMAF use ABR and MBR technologies, but WebRTC is not. Furthermore, in terms of cost, CMAF is cheaper than WebRTC. Usually, to reduce the latency, this is very common graph. To reduce the latency, we need to pay more something, such as computing resource. Or in order to get both benefits at the same time, we have to give up some functions like WebRTC doesn't support ABS, adaptive streaming. Yeah, this is a trade-off actually. So therefore, in the case of CMAF, CMAF is more suitable for the live sports event and live concert, whereas WebRTC live concert. But on the other hand, WebRTC is more suitable for the video conference and live interactive streaming. Actually, the main difference between media streaming and live video calling is the intensity, right? Live video calling and live video conferencing requires much more presence on both ends. The users interact with each other and are aware of each other at all times. This means that they are stateful in every possible way, which takes up computing resource. On the other hand, the media streaming doesn't have this tight coupling. We have two separate sessions taking place, the broadcaster and the media server and its viewers, right? And each with its one set of rules. There is a set of rules and capability optimization and needs. So we have to choose one of them according to our application requirements. Yeah. So if our applications pursuing live sports event and live concert, we have to use a CMAF or dash. But our application is for video call and conference and something like interactive streaming. It's good to use WebRTC. Good. Okay, so far I introduced about comparison between CMAF and WebRTC, and we learned about CMAF and WebRTC as the solutions for to overcome the latency issue of ABS, right? Okay, good. So now finally, let me explain about advanced video streaming. First, as I mentioned before, WebRTC does not support the adaptive bit rate streaming, right? This means that the end clients receive a fixed quality video stream. Therefore, in order to provide the different quality of video according to their device capability, the sender has to make independently different quality of video streams. And the intermediate server called SHVC decides which individual stream to forward to the end devices. So it calls Simulcast. This manner calls Simulcast. For the details about SFU, a selective forwarding unit, yeah, I will skip it today. But let's discuss more later when we have an opportunity. Anyway, this Simulcast requires more cost in the sender side because they have to make independently different quality of video stream by himself. So in order to reduce the cost in the sender side, we can use scalable video coding called SVC or SHVC. The sender sends just one single video stream, but inside there are multiple layers. Usually there are one base layer and multiple enhancement layers. So SFU decide which layers to forward to the devices. Likewise, if we use SVC for the WebRTC, and we can solve the scalability drawbacks of WebRTC. So the end device can receive the layers according to their device capability and their channel status. So that's why we can overcome the drawbacks of scalability in WebRTC by using SVC. Okay, good. Okay, maybe some students or people can wonder that can we use this SVC even in the MPEG-DASH or CMAF? Because MPEG-DASH already provides the scalability functions unlike the WebRTC, right? So I can say that yes, we can use the SVC for the MPEG-DASH and CMAF. So now let's see how can we use SVC in the MPEG-DASH. Let's see one example. There are two types of server, using without SHVC and with SHVC. So, sorry. Left one is the dash server and stores all of the different quality of video segments, because the server has to prepare all things to respond immediately to the user request. This is the conventional way. This is the traditional way in MPEG-DASH, right? On the other hand, the right one is the dash server using SHVC. So it stores only one SHVC encoded video segment, because this include multiple video qualities. So we can reduce the storage cost. We can reduce the storage cost, and it is more flexible to operate buffer in terms of receiver side, because in the case of in the receiver, they can choose one of them in accordance with their channel status and device capability. However, the encoding process of SHVC is more complicated than the normal one. Yeah, this is a drawback of SHVC, but we can reduce the storage cost. Anyway, let's see the example of MPD for the SHVC. Maybe now you are familiar with the MPD structure, right? Assuming that this is the two-layered video, one base layer and one enhancement layer. Since base layer can be decoded independently, the first representation, this one, the first representation is nothing special. This is the same to normal one, just a representation ID, a MIME type, video and MP4, and then codec. Yeah, they used. And however, in the case of enhancement layer here, it cannot be decoded without the base layer. This means that the enhancement layer should be decoded on the top of the base layer. So since the second representation depends on the first one, so we have to put the dependency ID here in the enhancement layer side. This means that V1, this one, the first base layer V1 is required to decode V2. And for the enhancement layers, we have to put additional information like LHV or LHE in the codec identifier. This means that they use the same codec using by using HEVC, but this is the layered video. So in the enhancement layer, we have to put more information like this. This is also defined in the MPEG-DASH standard or SMAF standards. So you can choose one of them by according to your applications. Yeah, that's all. So yeah, anyway, good. So far we learned about SHVC and then how to use SHVC in the WebRTC and in the MPEG-DASH. So, and now finally, let me introduce how to stream 360 panoramic video with low latency. Nowadays, there are many devices for 360 video, such as 360 video cameras and head-mounted display and so on. So, sorry. So when we capture the 360 video, one of the frame is like this, right? So usually for the high quality of 360 video streaming, we need 12K resolution at least. Again, for the high quality of 360 video streaming, we need 12K resolution at least. However, as you know, we only watch the part of the entire 360 videos at a specific time. Means that at a specific time, this red box is my current viewport. This is my viewport at this time, right? So therefore, many researchers thought that it is so inefficient to transmit the entire viewpoint because we don't need other views at a specific time. We just only focus on the specific viewpoint. So in order to solve this problem, first we can think that it's good to divide the 360 video into multiple tiles like this. And then we can send only tiles corresponding to the current viewport. For instance, if the red box is my current viewport, the content server only streams these 6 tiles, number 13, 14, 15, 21, 22, 23. Therefore, we can reduce not only encoding and decoding latency, but also bandwidth costs significantly. Sure, of course, this method also has many disadvantages because this is not optimal method. But this is the basic concept to reduce the latency for the 360 video streaming. First, we can divide the entire view into multiple tiles. We just send the tiles corresponding to my current viewport. Yeah, this is the simple way to reduce the latency and the bandwidth, right? Okay, good. So usually to this end, SRD, Spatial Representation Description, is used for identifying the tiles in the MPD. Maybe you remember what is the MPD, right? Yeah, MPD is very popular for you, right? Yeah, I think you guys are already familiar with the MPD. So MPD is the metadata of MPEG-DASH, including all information about the media component, right? So in the MPD, we can inject SRD information for the tile-based 360 video streaming, okay. Let's see one example using 4 tiles. Okay, there is assuming that there is a panoramic 360 video, we can divide it into 4 tiles, right? Okay, and then the panoramic viewpoint has the 8K resolutions, and that's why each tiles has the full HD resolutions. So in the MPD, we can put some special property like supplemental property in each adaptation. Maybe you remember that what is the adaptation set? Adaptation set refers to the each component, right? That's why each tile means each component, right? That's why for each tile, we need one adaptation set. So each adaptation set, we have to put the supplemental property like this. And we can put, and then in the supplementary property, we can put some numbers like this. Yeah, like this, in order to identify the location of each tiles in the entire video. Again, we need some numbers. We have to know where the first tile it is. So the first number, okay, so here the first number is an ID. So this is the tile 1, means that tile 1. And the second and third numbers, 0, 0, are a starting point, x-axis and y-axis. So this is the 0, 0, right? That's why, and then 1920 and 1080, this is the number for the resolution of tiles. And then final last 2 numbers are the resolution of entire video. Actually, using these numbers, we can identify where is the tile it is. Actually, this is everything to identify multiple tiles in the entire 360 video. Okay, now see, it's so simple, right? So when if you want to make some applications to stream 360 video by MPEG-DASH or CMAF, you have to consider the SRD in the MPD. So without SRD, you cannot transmit and you cannot stream the 360 video, video streams. Okay, good. Okay, good, right? So actually, this is the end of my lecture. So let me finalize these lectures. Okay. In the lecture yesterday, we checked what is the latency issues of current video streaming, such as MPEG-DASH. So today, we first learned about CMAF, which is big features for low latency. And CMAF can also reduce the many costs. And we also learned about WebRTC. That is like a session initiation protocol of VoLTE or VoIP, but it works over web browsers. It can achieve low latency rather than CMAF, but its scalability is low, and it requires high cost because of the well-known trade-off between complexity and latency. And finally, we learned about some advanced video streaming. First, Simulcast and SHVC for WebRTC. This is to improve the scalability of WebRTC. And finally, we learned about how we can stream 360 panoramic video with low latency. So we learned about so I introduced tile-based streaming and using SRD in the MPD of MPEG-DASH. Good. So I just only introduced the concept of CMAF and WebRTC and the advanced video streaming. But I hope you understand what is this, what is the WebRTC, what is the CMAF. So maybe if we have some good opportunity to extend this lecture, yeah, maybe I will give some information about in the lectures. Okay, good. This is the end of the lectures. So thank you for your attention. So if you have any inquiries, please feel free to ask me by email anytime. Okay, good. So let's check the. Okay. Do you have any questions in the chat? Yeah, sure. Yeah, I will upload the slide and video. Yeah, maybe today or tomorrow. Yeah, right.